So, good evening. Let me introduce myself. My name is Gopakumar. You can call me Gopu. I'm from Tata Institute of Fundamental Research. I am part of something called Indian Pulsar Timing Array, and we are integral part of something called International Pulsar Timing Array. You might have heard about these names. Ghulam gave a talk here, I presume. And I'm an associate of a place called Center for Gravitational Wave Universe in Seoul. I am going to talk about, with some equations, detection principles of various gravitational wave observatories. And I'm not an experimentalist. I'm not even a part of ASI. So you can imagine, I do some calculation. Okay, so I will give an introduction to gravitational wave polarization state. Professor Mohanty told me that he already introduced Einstein equation, linearized version of that, and then even HD correlations and things like that. Perfect. So I will give a slight recap of some of those results, and I will need how to obtain this gravitational wave polarization state to go forward to explain how interferometric hectohertz gravitational wave observatories operate based on general relativity arguments and physics argument, of course. And then I will talk about what's its difference between an hectohertz gravitational wave observatory and a millihertz gravitational wave observatory, essentially LISA, the cartoon, you have it in your poster. And then, of course, I will talk about PTAs and few other things that will, these 3 and 4 and plus a bit more will happen on Monday. And I'll try to get 1 and 2 under control today. It will be equations, but I'm sure that that's not a problem for you guys. Okay, and again, I have not discovered any of these things. It's all from masters I'm trying to reproduce for you. And I'm really grateful to, the towering figures in gravitational wave computations like Professor Gerhard Schaefer, Klaus Lametsal, Norbert Stroman, Bernhard Schutz, Bala Iyer, and many others. You can see that these are somewhat senior professors you may not be familiar with. So you can imagine that I'm also fairly senior. And then, however, if there are some problem, you did not get it, and all that, the blame is on me, okay? They didn't teach me those things. Okay, so I'm directly going to gravitational wave polarization states. So let me kind of give a recap. In 1916, Einstein predicted existence of gravitational waves. So we will try to go into those kind of equations to begin our journey. So essentially, that his argument for the existence of gravitational waves are based on his linearized vacuum field equation. And he was a big fan of Maxwell. So you will actually see this, comparisons in the linearized Einstein field equations. So let me get into that very briefly. So when I say linearized vacuum field equation or linearized Einstein equation, the space-time is essentially given by eta mu nu plus h mu nu. Eta mu nu, that's some Gaussian guy. So essentially, we demand that h mu nu to be so small that all expressions can be, linearized. We keep the leading order with respect to, h mu nu and their derivative. So we will only keep terms which are like h mu nu or its derivative, space-time derivative, obviously. The space-time is very, very close to that of special relativity. That's the game here, okay? So, and then, since I've been talking about h mu nu, I would like to introduce, I think Mohanty might have talked to you that too. So it's actually useful to introduce a gamma mu nu, which is essentially h mu nu minus h eta mu nu by 2. And h is this, of course, the, determinant of h mu nu, and I define gamma. So I'm just trying to do most of the operations. I'm going to use eta mu nu. So you can see it's fairly straightforward. I explicitly gave that 4 to show that this is essentially gamma is the same as minus h, kind of a trace reverse if you want to think about it that way. So h mu nu, I can of course write it like this in terms of eta mu nu. Why I need it? Because then I can plug it into Einstein field equation in vacuum. So if I do that, Einstein field equation essentially became the box operator gamma mu nu equals 2 times kappa T mu nu. Kappa is the Einstein's gravitation constant in contrast to Newton gravitation constant G. And it's important that in order to, the Einstein field equation, I'm sure that Professor Mohanty explained that to bring it into this box operator, you need to put gauge restrictions. And the one I'm actually imposed here is this one, dou mu gamma mu nu equals 0. And this is so-called the Hilbert gauge. So there are several versions of names for this. People call it Einstein gauge, Fogg gauge, and even de Donder gauge. So those who are familiar with post-Newtonian, you will find that expressions are in ADM gauge or in DD gauge. That DD, initially I thought that was the more Derivel, but it's actually de Donder. So, but important thing is that this equation, because of the box operator is hanging around, are invariant under Lorentz transformation. That's very important. Why is that? But then you can bring in techniques of electrodynamics to take a look at this. So that's the game, and Einstein was extremely happy with that. And so you can see the gauge freedom of linearized gravitation is very, very close to how we deal with electrodynamics. And so the Maxwell's equation can also be, written in terms of the box operator, in terms of a mu nu, or sorry, in terms of the vector potential, or a mu, and the scalar 1. So there's a one-to-one comparison here. I'm not going to go into the details here. I'm sure that you can look into it. But if you are interested, I will be happy to do that. So you will see that you actually need that kind of 4-vector to go from, to come into that linearized version in the de Donder gauge. And you can see how the h mu nu varies transform under that kind of coordinate transformation and things like that. So the Lorentz gauge is essentially generalized. This I took it from another lecture of mine, so I didn't bother to change the notations and all that. But the idea is that it's one-to-one correspondence. Okay. Okay. So again, the influence by now the electrodynamics, because I have one-to-one correspondence of most of my equations. One is a kind of 4-vector. This is a tensor. So you have a general solution to the linearized Einstein field equation, essentially a superposition of plane harmonic waves. So that's essentially given by, this is the form. So I think I should have put, it's a 4-vector. So you can see that's the real part of a mu nu e raised to I k rho x rho. Is this too much equation for you? I can't really go without this, or but I'm just giving the steps. It's fairly easy to work out. I have given most of the steps in between. So the important thing is that this is a real covariant vector. However, a mu nu can be a complex but symmetric. And then this condition can be imposed. This is essentially, because we are working on the box operator, you can see that I'm just raising and lowering with eta mu nu here. So this essentially says that if, do I need to say this? This becomes a problem because I should have used ijk or something. But anyway, so you can see that eta sigma tau, this, you get 2 time differential not time, because I'm doing dou mu and dou tau and dou sigma. So you can see that I times I is the imaginary, k sigma I times k tau, and this has to be 0. And we know A mu nu cannot be 0 in general. So this can only happen when this condition is imposed. And that's very nice. So it says immediately that I have a light-like covariant vector. That's a special relativity language. So essentially what you're saying that you part of your plane harmonic wave as a 4 vector that is light-like. Again, going to the electrodynamics, you don't want to go away from electrodynamics, but you can come up with this nice interpretation. So another way of saying is that the gravitational waves, if you consider the solution of that box operator, which we identify to be gamma mu nu as a real part of this, we can argue that because this is light-like covariant vector, gravitational waves propagate on Minkowskian space-time with the speed of light, c, just as electromagnetic waves in vacuum. So we have not done anything amazing here, just use the equation here and there. It's all inherent in those conditions. I'm just trying to explicitly state those things, okay? Okay, so that's for the box operator condition on our plane harmonic waves. I can do ask the question, what are the consequences of the de Donder gauge or harmonic gauge or whatever. So then I can again run the same argument here. This time, of course, I have one derivative here. I wrote it like this. Then it becomes, it's not that difficult. You can see that in order for this quantity to be 0, I will have to have k mu a mu nu to be 0. So this Hilbert condition sort of restrict possible values of a mu nu. You can't go, of course we said that a mu nu is to be same as a nu mu. Fine. It can be complex, but we have better because we have the de Donder gauge condition, and it tells you that this has to be 0, and that is a restriction. So the number of components for a mu nu are not, it can't be 10. Okay, so it restricts possible gravitational wave polarization state. That's the statement I'm going to make, and I will go through this argument. So clearly we are talking about space-time, so it's a 4x4 matrix with 16 entries, but I already imposed the symmetric arguments. That gives you only 10 of them are independent, right? That's a matrix argument. But I already imposed the Hilbert gauge and showed you that there are 4 scalar equations. This, because mu it's a free index, right? Nu varies from 0, 1, 2, 3. So there are 4 constraints, which simply means that there are 4 scalar equations. So there are 4 more constraints, not 10 independent, because there are 4 more, it's 6. So it looks like there are 6 independent polarization state possible for gravitational waves. Actually, that's not the case. Why? Well, it looks like we have not finished all our gauge freedom possible, and it's a subtle thing, and I will try to explain it in some detail because it always confuses. It really confused me, especially from when you read very concise things in a classical theory of fields. So the game is that you can actually introduce a constant for vector, constant for velocity vector. So that's what it is. It's minus c square, and we'll take a look at this, what actually meant by all that. Then it turned out that it's actually possible to make another coordinate transformation such that the Hilbert gauge condition is preserved, but additionally you get very nice constraints like this. You get u mu, that's a constant for velocity vector, a mu nu should be 0, and a mu nu can't have any trace. This is essentially an expression for trace. So this is, you can see that this is some sort of a 4 vector, 4 velocity vector kind of, it's dot product. So This is what we call TT gauge. In fact, the interferometers is actually much better. You can actually say that gravitational wave observatories actually work in TT gauge naturally. Okay, so this turned out that there are 4 constraints. This is a scalar constraint, no trace. That's one equation. The other one, you have 4, so which simply means that you don't have that kind of 6 degrees freedom, but you get essentially 2 gravitational wave polarization in this specific gauge. And I will try to argue that indeed it's possible to do that coordinate transformation, because that's critical for our discussion, and I will try to do that. Does that make sense? Okay, so just the way we wrote the linearized Einstein field equation in a very specific gauge, Fokker gauge or Didonder gauge, allows us to argue that there should be only 6 independent components of A mu nu, which is the solution. That's the summary I'm talking about. But it turned out that Einstein relativity allows further gauge freedom, which allows us to simplify things, and this is what happens. So therefore, out of that 6, I already provided constraints, so then I get only 2 gravitational wave freedom, and that's in the new coordinate. And this is turned out to be the last, kind of transformation I can do. So this kind of arguments are there in even classical mechanics. So you are familiar with the mu going around, the reduced mass going around the total mass, right? So that's a Newtonian classical problem, right? So you have M1 and M2. I can map that into an effective one-body problem. So that's mu moving around M. Very nice. So the question is that, can you show that it's a closed orbit? So you have, mu is the only guy moving around. So if you look at the phase space argument, there are 6 degrees of freedom, okay? But mu is not allowed to go that kind of freedom. Then you will say that, well, energy is conserved, angular momentum is conserved. So that's 4 of them, which means the phase space is 2-dimensional. That's also a problem. Then it will be entire plane. And that's precisely what actually Mercury does. Okay? The orbit will not close on itself. This simple argument is actually mathematically profound. So in Newtonian dynamics, you have this, you have this, you don't have this. Okay? So there's something else going on there. So you came up with this argument, mu going around the mass, okay? In the phase space, 6 dimension, conserved quantities, you count energy, angular momentum. Don't worry about center of mass because I already moved. So that's 4, which means I should be doing this. But I usually do this. We can show that. The reason is that there is an additional vector which is conserved, and that's the amazing thing. Have you heard about that? Laplace-Runge-Lenz vector, right? But be careful, because that's a vector. It has 3 components, right? Then none of the planets should move. Earth should not exist. Well, right? I mean, 3 components, so 3 constraints again. No. Turned out that that vector has only 1 free component and allowing you to get. So this kind of arguments are there, so it's somewhat similar. Okay, so we need to demonstrate that it's possible for us to have the TT coordinates. How do I do that? Well, the idea is to perform a coordinate transformation. So the x mu goes with this new coordinate with the help of f mu, and which of course I'm going to, because everything has to satisfy the box operator, therefore the possible solution can be real part of I c mu e raised to I k rho x rho. So you have a, so I again introduced that, got back that covariant vector k rho. from our harmonic wave solution, and then we want to choose C mu, that's is a 4 index object, such that the condition I just mentioned, traceless and U mu, A mu nu should be 0, should hold. That's all I'm going to do, okay? So the game is to choose this new coordinates such that the C mu, because everything else is known to me, K rho I already got it from there. So I need to demonstrate to you that it is possible to choose some C mu like that, and it has a very specific form. And the question is it possible? Well, I need to know how the gamma mu nu should vary. This is a, it's a tensorial object, so it's not that it's a covariant. It's fairly straightforward, this kind of, to show that eta gamma mu nu should vary like this, minus minus, it's a tensorial transformation. Then, but I already have a form for gamma mu nu, so this goes like a mu nu raised to k xo. This, I have to do this calculation, and that's because I already introduced the iota. I have this iota I twice, that's complex I, okay, not iota. So you can see this one with respect to nu, so I get the k nu. This one with respect to mu, I get this eta mu nu I times k rho c rho. So this is how under that coordinate transformation A mu nu varies. Okay, so and it's not that difficult for me to actually show that A mu nu should vary like this, because this minus, so it's not, there's nothing going on there other than that. So eta mu nu. So the question now is that, can I choose C mu such that these two conditions, right? Remember, this guy need to be traceless. That's the traceless condition. This is that, how will I say? It is that propagating, orthogonal condition. So that's the U mu, A mu nu should be 0. So, but I have these two conditions. The question is that, is it possible for me to choose a, C mu which satisfies these two conditions? Well, I can always choose my for velocity vector to be like this, C 0, 0, 0. And then I'm going to consider, in order to see whether T1 I consider the spatial component, the condition something like this. And it's not that difficult for me to actually then show that Cj, the spatial component of C mu, is essentially given by the A0j, which, where I had that 6 independent polarization state, those A mu. I have that formula like that. So it's clear that Cj are essentially determined by C naught. The question is that, can I get C naught in terms of my A mu nu and K? So I go and look at the nu equals C0 of the condition. This is what I get. And it's not that difficult for me to actually show that this is nothing other than K mu, A mu nu equals 0. That I already know. So this is not going to give me any additional information. It shows that, well, that's what I expect. So that's fine. But then I can look at, can I impose the condition, that, I showed you this here. This is the trace condition. In the new coordinate, this has to have no trace, eta mu nu of that transform object. This essentially becomes eta mu nu, A mu nu minus 2 times K rho C rho. So I'm going to look at that condition. So that's what I'm saying. I'm trying to fix C0 using that T2 argument. And if I run through the algebra and I left those algebra there, I will find that C0 can be written in terms of the A mu nu I started with and the Ki and A0j. That's very nice. So therefore, using my existing gauge, I can indeed construct a C0 following this expression, because it's based on the condition that it should have no trace in it. I should lead to C0, which of course C0 once known, I can get Cj from this, and therefore I can ensure both T1 and T2 are satisfied in the new coordinates. So the question is that, remember what we did was, the game was to go to a new coordinate with the help of this function and the old coordinate, and I showed that this C mu can be written as quantities k rho as well as a mu nu of that old. Okay, so I can choose that, and which satisfy both this condition. That's non-trivial if you think about it, and that's the game. So it is possible for me to go, I can have the Einstein field equation, impose the Einstein gauge, get the box operator, and show that the plane wave solution has 6 independent degree of freedom. Using those quantities, I can go to another frame in such a way that these additional 4 conditions are imposed, which are what I call TT gauge, and that gives me indeed that new coordinate where I only have gamma equals 0 and h mu nu is the same as gamma nu, and this condition is what I will be operating on. So you can see that there are conditions to ensure that I have only 2 independent degrees of freedom for a mu nu, and these propagate with the speed of light, and I have the freedom to choose u mu to be like this, the for velocity vector, and the wave vector can be omega c over c. This actually satisfies the condition I was talking about here. And if I have another kind of for vector, I can choose, because background is Minkowskian, I can go via Lorentz transformation to such a form. So that's fine. I have the freedom. That's important here. And therefore, and then I can look at in the TT gauge, transverse and traceless, I have these conditions imposed. This is the condition coming from the, K mu, A mu nu should be 0. That's what this is. T1, this is orthogonality condition, transverse condition. I get C E naught. And this is the traceless condition I impose. And if you look at this carefully, it's not that difficult for you to actually argue that the only 2 non-zero components, because you have to satisfy these things, are such that A11 should be negative of A22, because it turned out that you can't have these guys, by looking up, you can actually show that they cannot be there. So then that's we call plus, and I will talk about why it's called plus. And then A12, by default, it should be A21, right? That's symmetric argument. That's called cross. So there are only 1, 1 and 1, 2 components are non-zero. Sort of essentially demonstrate, because the 4 vector I was talking about was actually going, to the, if you look at that, it was along the C. So I have things which are 1 and 1, 3 are X, Y, C, if you want to think about that. Okay. So, and there are only 2 independent polarizations too. So these are essentially what the gravitational wave I'm talking about. And this is the gauge I will be operating, and for, all these calculations and things like that. Okay. Okay, I think I've been slightly ahead of my time. That's all right. So why am I calling them? And I will give an explanation for that slightly later. Not to confuse you for something else, but if I take a ring of particle, because the gravitational wave are essentially a non-local effect. So unlike electromagnetic radiation, I can't, electromagnetic radiation is very nice. Take a point charged particle. If there are passing electromagnetic waves, we know how these guys will move, and I can infer it's a dipole, quadrupole, or whatever. But that's not the case, because the general relativity essentially is a tidal interaction. That's the measurable quantity, and you need local measurements to see the tidal interaction. That's the reason we actually take a ring of particle, and if you assume or imagine the gravitational waves are propagating perpendicular to this plane, this gets deformed, and I will show you how this deformed like this later. And this is what I said, 1, 1 and 1, 2 components. So they are along x and y. So you can actually see that they get deformed in a very specific pattern, and that's the reason they are called plus and cross polarization. But that's all very nice. So, but we need to kind of come, this is all polarization state. I reached there, but now I need to go to the next step, which is to use this to sort of interpret gravitational wave observatory, and we will try to do. I need a few more, inputs which is easy for me. With those constraints, I can actually, explain things neatly. So, I would like to look at x0 lines, namely the word lines of x mu tau, which x dot mu, which is the u mu which you saw, are geodesics. I would like to demonstrate that, especially for a metric which is eta mu nu plus h mu nu, which the condition imposed. So one can do all that. So this is x dot mu this is a constant, and x double dot is 0, because remember the u mu I just chose like this. So if you take the derivative, proper time derivative, it will be 0. Another way of saying is that if you look at the x mu, it will be ct with a constant vector, spatial vector. Okay, so that's the genesis of this, and I need that for some calculation purposes. So if I have this, I can do the Christopher symbols. It's a straightforward calculations. If you have Maple, you can do this by hand too. This is what I get. I'm again going back. I can see that I'm using gamma, and I'm using the solution for gamma, because we are all dealing with gravitational waves here. Otherwise, it's Minkowskian, so nobody is interested. Then I find x double dot, because that's what I'm geodesic equation I'm after. I can work out this, because once I have the Christopher symbol, I can compute this, and you will actually find this is 0, x double dot mu, by virtue of u mu being a constant for vector, velocity vector, that's 0, but then I have to have this. But you can see that this is also 0, right? Because if you look at this, a mu nu, nu sigma, and u sigma, that should be 0. That's what we talked about earlier. And similarly here, so these terms by default, since I'm in TT gauge, this is 0. So another way of saying is that if I have word lines x mu of tau with this condition, they are geodesics. And that's important for me. And I need that condition to explain a few things. Just want to show. It looks trivial, but think about it a bit more. So what's the picture here? So geodesics are, so I can associate x0 lines going through the origin as well as going to a point which is, slightly away from it, xi, spatially, okay? So x0 lines are word lines of freely falling particle. The reason why I'm going after freely falling particle are all observatories are trying to create as best as possible freely falling particle, then that can only respond to, gravitational waves. Freely falling, that's a very important thing here. So it's easy for me to say this mathematically, technologically to demonstrate is what it costs thousands of crore, okay? So that's the game here. So x0 lines, I'm talking about one through the origin, one through this, are the freely falling particle. So the important thing here is that the spatial coordinates remain the same. What does it even mean? It simply means that if I have, interferometer, and I'll come to that, the n mirrors and all are fixed coordinates. So this is something, that's the reason I've been very careful not to bring in those geodesic deviation equation to confuse you further. This does not mean, so these spatial, this will be 0, 0, and this will be x, y, z if you want to call. I mean, I just use x1, x2, x3, it's the same. This does not mean that gravitational waves have no effect on freely falling particles. Their spatial coordinate remain the same. If they are at the origin, they will remain at the origin. If they are at some delta L, they will remain there. However, that doesn't mean anything. What I need is that I need to measure the distance with the help of that metric, and you can show that that distance will not remain a constant. And that's the calculation I'm going to show and kind of connect that to interferometers. Okay? So how do I do that? This is fairly straightforward. So the square of the distance between x0 line at the spatial origin and the neighboring point. That's the one I'm talking about here. This is the spatial origin. This is that XYZ point, neighboring point. Okay. Important thing is neighboring, and I'll quantify that down the line. So imagine that xi, I means spatial index only, are small. So the metric can be viewed as a constant between the origin and xi. Okay. So therefore, I can compute this quantity Gij x0, 0, 0, 0, xi minus 0, xj minus 0. I'm going to be very explicit here. And of course, I know what Gij is. It's in my TT gauge. I'm going to write it like this. Very specific, okay? Delta Ij is not that difficult for me to show you. This is indeed delta Ij xi xj plus real part of Aij xi xj e raised to I k0 x0. It's not that difficult to show this. Just, it is obvious, but if it's not obvious, just sit down a bit. And then, but this I know. I just showed you how to compute this because we have already determined non-vanishing components of Aij, right? We told you A11, A22, A12, A21 minus and all that. I can compute this. Oh, this is an Einstein summation convention, okay? I assume this is gone. So then it just becomes a plus x1 square minus x2 square e raised to minus I omega t. This one will be x1, x2 e raised to minus I omega t. Another way of saying is that square of the distance between x0 line at the spatial origin as well as a neighboring point is essentially given by this. It used to be the chronicle delta of that tiny distance, but passing gravitational waves modify this. So this is like the circle, and these are the elliptical deformation. And that's precisely what I showed you, that these are called plus and cross polarization, right? So you can imagine that this is like the radius, if you want to think that way. So these are the deviation of that, and that's elliptical deformation. And that's precisely why I have that plus and cross polarization, where the circular ring of particle got elliptically deformed. Okay, but we can be very more specific, and I will show you at some. I don't think I will last till 6. Yeah. Okay. Okay. So this is the point. But again, so imagine that you have particles that are arranged on a spherical shell. So that's the operational thing. How does it work? So, just like I showed you, initially I have a spherical ring of particle, and again, free particle, that's very important here. And if I let them go, and they are free to move in that frame, in that plane, then passing gravitational produces time periodic elliptic deformation. Just want to emphasize that point, okay? Why? These are elliptical deformation. This used to be circle, and it's a slightly different way of saying this, essentially the same thing. Okay, and that's the result I'm going to use to explain LIGO, and I will stop for the time being and just go back to show something. Okay, so you might have heard about Michelson interferometer being used, right? Okay, I can slow down slowly. Oh, so if you have questions till that, I can delay a bit more, and then, yeah. Okay, if you don't have questions, then I will proceed, but catch me. So gravitational wave observatories are typically Michelson interferometer. That is a additional term you might have heard, Fabry-Perot cavity. Have you heard that? Okay, we'll come to both aspects, but not more than that. Okay, that's where, don't ask me how the laser works and all those things. We will not go into those. I told very clearly that to you to Koushik that I will know. So actually, the idea of employing Michelson interferometer for detecting gravitational wave was actually suggested before most of us in this room were born. It includes me. I'm still, as Bala keeps saying, fossils, but so that's almost 62 years, right? 63 now. But influenced by Braginski, in 70s, somebody called Forward actually built a small interferometer. But this is, I love to say this, the construction of this big terrestrial gravitational wave observatories like LIGO, GEO, Virgo, TAMA all started in 90s when we were your age, just after Joe got his Nobel Prize for the binary pulsar. There's a correlation. Anyway, many people were critically instrumental. Rainer Weiss, Ron Drever, Kip Thorne, and the list is huge. So, but what does it even mean? I'm sure that Michelson interferometer you came across for the IISER experiment, or you might have done this for measuring the speed of light and all that. So it's essentially you have a beam splitter, the laser beam enters, and the beam splitter splits the beam along two orthogonal directions. They travel distances d1 and d2, reaches mirrors m1 and m2, returns back, and usually there will be a detector to look for the fringes, and you need laser. How many of you have done this without a laser? Not the front row people. These days you guys do this with laser, right? Have you done it with sodium vapor lamp? No. So they don't, of course we have done it. No, you don't count. So lasers were very expensive when we were your age. So we have to take a sodium vapor lamp because one of the wavelengths can be sort of extracted from that with and then used, so that's a coherent wave source. And then it's possible for the interference to, the theory of interference says that. And how do I measure? Well, I look for the interference pattern to kind of measure and we will get into that. Okay, you are familiar with this, right? Okay. So if the Michelson interferometer is actually operated in vacuum, the phase difference can be computed. It's not that difficult. It's essentially 2 pi divided by lambda times d1 minus d2 times 2. 2 comes because you are going this way, coming back, and there's a difference, okay? So a typical, well, these days are all sophisticated, should be able to measure phase differences up to 10 raised to minus 5. Kind of 1 part in a million is a typical number. And you can imagine immediately why this is exciting. And how do you measure those phase differences? That's with respect to the fringes, how those things move and all that. I have done it, but I can't remember of it. I said I will prepare and have a slide for that, but I couldn't get time, so I didn't do it. But somebody should teach me. So the game here is that the lambda is of the order of 600 nanometers. We used to say angstrom, but now it's nanometer. So you can see that this delta phi of the order of 1 part in million, you can see that the d1 minus d2 can be considerably smaller than angstrom or nanometers. That's exciting. So interferometer are allowed to measure slight variation in the spatial coordinate, the effective length or proper length because of this property, okay? This equation. That's very important for the discussion here. And so this is how it operates. So it's important that we have the beam splitter M1 and M2 are allowed to move freely in this plane of this thing. Okay, so ideally gravitational wave should come like this. Obviously it's not going to come that, but okay, this is for the government work, that's good enough. So we can assume that, and then under the influence of the gravitational wave, the mirrors will move, and that motion should be unobstructed by other interferences, not interfere, So then we can consider this as the particle at the center of the TT frame I'm talked about. M1 and M2 are on the either x-axis or y-axis. It doesn't matter that I'm going to flip. Okay. So now I'm going to connect. So what I'm going to do is that I showed you that world lines, right? Origin at xi. That's it. That's origin. This is my M1. I can flip that and get the other one. Okay. And I will going to compute that quantities when the gravitational wave passes by. So, recall that the distance from origin to a particle with coordinates xi, we actually computed this like this. And since I'm talking about plane waves, it was not going to depend on x coordinates. That's the reason minus omega t. I'm going to restrict to plus mode because that's easier for me to do the calculation, but you can do this in general. Then I get that distance, essentially delta x, delta, the chronicle delta KL XL, XK XL, like this, because I'm taking the real part of this. And that's for the mirror M1, but I have for the mirror M1, there is no y contributions around the x-axis or the z, so essentially I have that to be 0. So I get d1 square essentially to be this. And I can do for the similar one, and I can do that for the mirror 2, where x1 and x3 are 0. Then I get a equation like this. So essentially it shows that if I consider this as the unperturbed, because these are perturbed by gravitational waves, I can consider d0 to be either x1 square or x2 square. I can rewrite this expression like d0 square 1 plus a plus cos phi of t minus some initial phase phi, or I should have, okay, I think this is good enough for them, So because I'm saying it's the same guy, so I get that. So then I can go and compute the phase difference. Remember, this was the formula I used. 2 pi by lambda, I put the 2 there, so that's all right. And I get square root. But square root is a non-linear operation, and I say everything is linear, right? So I can expand that. This is just a Taylor expansion. So I get half of this, half of that, 1 minus 1 cancels, and I get this quantity here. So the delta phi, the gravitational wave induced phase difference, is actually proportional to d naught. It's proportional to a plus and all that, and it's of course inversely proportional to lambda. So this equation, and you can imagine that the delta phi is something like 1,000,000 or better. So if you want to measure tiny changes, clearly you need to have d0 times a plus should be something. So you need long arm length. You cannot have a gravitational wave observatory with a centimeter or something like that. So this will go into kilometer, okay? And by the way, this lambda is the wavelength of the laser use, whereas this omega is the gravitational wave frequency. It essentially modulates, cos and sine are modulated. So that's all it, okay? So it modulates the interference pattern. And that's how all these experiments are trying to do. Does that make sense up to here? And I have stolen slides from, this is actually from LIGO. This is from Alan Weinstein, who actually came many years ago to India to give a bunch of lectures, and I flicked the slide. I was in the audience, so naturally I have no idea about these things. So this is actually, this guy works, and we will come into this. So that's the laser, And more importantly, you can see that he put a black thing, and that was fantastic. I see when we operate our Michelson interferometer, we were looking for, the fringes. We operated on the bright spot. That's not how LIGO operates. It actually operates in the dark port. Nothing will come out. Okay, because if that's the sense state, gravitational wave passes, then it will take it away from the dark port, and you get some furious, waves. That furious light photons, and it fluctuates with time, and that's your gravitational wave. So the gravitational wave observation is very trivial, actually. You operate like an interferometer like this, pitch dark. Output of the interferometer, nothing comes out. If there's a passing gravitational waves, you find some stray photons, which you can actually measure. Picking up things. And then that light, and these things only fluctuate for milliseconds. And when you analyze that fluctuating light, it changes in amplitude and frequency. We say, wow, we see gravitational waves. That's how we measure gravitational waves. There's nothing going on other than that. Only thing is that two guys should see it together with some delay. Otherwise, nobody's going to trust anything. So I have a colleague, younger colleague, and when the LIGO was being kind of commissioned for the O4, one was operational, and he actually kind of messaged how good the signal, beautiful chirp signal. He said, can't publish. It's only one, right? Nobody's going to trust you. So, but it was nice. I mean, okay. That's the reason LIGO is actually seeing more than 200 events, right? I mean, these are transient, last for milliseconds. Those milliseconds are essentially here. This fluctuating light, flickering light, which kind of, what's the frequency? It's roughly varies from 30 hertz to, a few hundred hertz, not kilohertz. You don't usually reach them, okay? And the effective gravitational wave as a deviation in the space, which we just, demonstrated. And you can see that that's the dark port I'm talking about. You can see that then this light start appearing. And the longer the light path, larger the phase shift, right? That's very important here. So you can see that this D naught, if it's larger, you get more phase. So that's very nice. So the game here is that the path should be as long as possible. So you can look at the typical numbers, for example. So most importantly, as I told you, my M1, the beam splitter, are according to our theoretical calculation, are freely falling particle geodesic equation. I showed you that, right? So the game is that these are suspended pendulum, because it turned out that the pendulums, can become free of external forces if you are good at it. And why? Because if you can suspend things by a pendulum, the external disturbances can be sort of, detunated or something like that. I forget. Yeah, so essentially it can be damped. Other perturbation can be damped, so it will actually freely move. So if you have a 50 centimeter pendulum length, then we know that F naught is around 0.7. So if you suspend a mirror, it will be free because other things will kill it around 100 hertz. I mean, 1 hertz. So, okay. So you can imagine that interferometer is sort of sensitive to around 100 hertz gravitational waves, which is not bad because one can actually show all black hole binaries are self-gravitating systems, and all self-gravitating systems should follow omega square r cube equals gm. Okay, m is the, so in the case of mu moving around the total mass in the two-body system, this is followed. This is the radius of that circle, this is the total mass, and you can actually show this, okay? And it turned out that if you really look at it, in short-shell coordinate, this also follows there. So it nothing to do with the sum constraint. Anyway, so and if you put and black holes have, so you can see that the R has a restriction because the last stable orbit. So if you can play around with this formula and ask the question, the gravitational waves, Professor Mohanty might have told you quadrupolar. So if this omega gravitational waves will be twice the omega, because the quadrupolar means xi, xj, and you take the derivative, it becomes twice. So then you can show that if you have a mass m and a self-gravitating object, then the peak frequency is actually inversely proportional to m square root. Okay, so that's very easy to show. I will actually slide in Monday, I will show that formula. Therefore, if you have stellar mass black hole binaries, the frequencies are going to be somewhere, the peak frequency will be few hundred hertz. And LIGO was interested in such system, so the 100 hertz makes very good sense. And if you 100 hertz gravitational wave, you can ask the wavelength of the gravitational wave, that's around 3000 kilometers. And therefore, and the strain induced will be h delta L over L. So all we are going to say is that delta phi is, I can rewrite this as 4 pi times L times h divided by lambda of the laser. That's the kind of phase. Forget about the modulation by cosine. So if you really want to measure small h, you need large L. And L cannot be too large because this is interferometer, the phase, right? We are interested in interfering pattern. So if you consider kind of sinusoidal thing, that if its L is too large, say more than lambda g over 4, wavelength of the gravitational wave divided by 4, you can see that the gravitational wave change sign, it goes up, goes down, 4 times, right? That's what I'm thinking about. So therefore, one guy goes, we want, and it comes down, it goes out. But if you make it too large, it's not going to help you. So then you can get cancellation. So you want roughly optimal length should be lambda g over 4 so that you are safe. So it's like the cosine sine, right? You don't want that scenario. So therefore, lambda g over 4 is at optimal length. But that's around 750 kilometers. So gravitational wave observatories should be 750 kilometers. That's problematic. These things cost a lot of money. And we know that you heard popular lectures before coming, or I'm sure that everyone, it's around a few kilometers. So what do you do then? And that's precisely where the Fabry-Perot cavity comes. It's a fantastic idea. So for practical length of gravitational wave interferometers, like 4 kilometers, the only way the phase sensitivity can be increased is to make the laser beam to travel those extra n times. In the cavity, you can see that. So here, you can see that the laser was coming like a small line, but here it become thick. Essentially means I'm pulling it up and down. So the game here is that number of times the light hits the mirror should be substantially large. And there is this fantastic idea of Fabry-Perot cavity, because you can actually create such cavities. They're very sensitive to the lambda, so that if the lambda is this cavity slightly changes, it kicks out the laser beam from that cavity. So that's the thing. I'm not an expert, but you can imagine that it's possible to do this. So if the light is phase shifted n times single pass length, that's the game here. And but again, you are not supposed to make the light path arbitrary. You can say that, okay, since I can do how long, instead of that n. So it turned out that the n turned out to be around 200 for LIGO. It's 800, something roughly we talked about. 750, 4 kilometers, you get 200 times. So the argument is the following here. The time for light, to leave the beam splitter, you remember this is the beam splitter. It leaves and gets into this cavity. because there are special, you can see that there are special coated mirrors here. This allows this guy, and then there are very clever way of doing all these things, which I'm no expert to explain you properly. You should listen to Alan Weinstein's lectures. If I spend 3 weeks, maybe I can reproduce that for you, but it will be so imperfect. But he does this amazingly. So you can see that it do this very nice. And then, so that's what they call tau storage, which is essentially 2 times n times L divided by C. N is the number of times 2L because, no, L is this, okay? So during that time, the gravitational wave again may reverse the sign, which you don't want, so which will be disaster for you. So you can see that t period of the gravitational wave by half. So 1 of 2f. So hectohertz gravitational waves, this kind of pole frequencies around 100 hertz is called the knee. There's a reason for that. So you might have seen the sensitivity, it is called a bucket. Okay, so this is around, I'm very bad at here, this is around 70, 100 hertz. This is around 100 hertz. And then this is around a kilohertz, actually smaller. And here this is like 30 hertz onwards. The reason is that the Earth is a big, nasty vibrator. Okay, so and it starts doing this around few hertz, so you get the effect. So even if you have suspended pendulums or array of pendulums, your mirror will not be a free particle that I want in my TT gauge at lower frequencies. Therefore, you don't go that. So this is the kind of knee frequency Alan is talking about there. So you can put those things and you find, once you know the knee frequency, I can put that and the T storage, and then I can obtain that N. It's around 200, which makes sense, right? We talked about the length of the interferometer should be around 750 kilometer. Well, if you have 4 kilometer arm length and you multiple times, you get 800. Again, roughly, but good enough. You get the idea. That's more important here. So, yeah, so that's the reason. That's how the gravitational wave observatory works. And how much time I have? I have, okay, I have plenty of time. Good. And so this may look slightly different from people talk about, gravity. Usually popular gravitational wave talks, yes.
Can I ask a question?
Yeah, sure.
So I guess in practice, n is a random quantity, right? The number of times that an actual beam of light will reflect.
No, so they actually choose the material and the frequencies because there are lots of things you can see that this laser, they do all sorts of detuning and all that thing. There's a huge setup here so that these guys can hang around 200.
Yeah, I'm asking is it precisely, if I send a pulse in.
No, not precisely.
So what's the spread around
200?
delta n?
I have no idea. See, that's what I'm saying. I'm not the master here. Yeah, but again, it's a good. I can ask some of my friends. Again, this is all. Again, the properties of the mirror are not dynamically changing, and the frequency of the laser, which they stabilize very precisely, are also under control. Therefore, my answer will be it will be around 200. Depending on how long you can sustain the cavity, because this cavity gets a massive disturbance that happened in 1708, 17, if I interpreting it correctly, because during that in spiral you get a huge blip glitch, which is kind of took it away from the the optimal configuration and things like that. Again, I may be bluffing a bit here. That's not my, but this is all I know. So, but I should, what's the error bar on? And it's a good question. Answer is, I don't know. Okay. So, because I just want to emphasize that it's not that the mirrors are, stretched and, yeah, stretched by passing gravitational wave. That's not the way to think about it. So this time delay is very important because it's actually going to work for LISA as well as the PTA. I prefer to go this. And Bernard Schutz actually emphasized these points in many of his lectures. So each arm may be treated as a clock, Einsteinian clock, whether you use a laser, a cavity, or a LISA, where you have to do time delay interferometry, or you use noise analysis of the pulsar data. Essentially, you are creating an Einsteinian light clock across these observatories, and we compare timekeeping of each arm with the other as they are stretched by passing gravitational wave. That's the way to think about it, because we are not measuring these distances between the mirrors at all. And I want to emphasize this point. It's slightly subtle. The argument, so it's incorrect to imagine that Michelson interferometer is essentially measuring the number of wavelength of light that fit along the arm. That's not at all we are doing. And he gives this beautiful argument. So it's not that, when you say one arm is stretched, other is, kind of compressed by passing gravitational waves. We may imagine, and many of the colloquium speakers will have to do that because it's very difficult to explain this way. So what does that even mean? Then people may imagine that the interferometer guys, what are they doing? They are actually measuring how many number of laser wavelengths are actually fitting this. So this may be, I don't know, some million, and the other one is million less one or million plus one or whatever. That's not what's happening. Why? If indeed we are doing that, we need our light to be stable because H is 10 raised to 21, right? So we also want our light frequency to be stable in one part in 10 raised to 21. I can tell you there's no such light sources available for you. Okay, so that's not what we are doing. And so it's not a length measurement. I just want to emphasize that. However, it gets connected, but you need to think these phase differences caused by time delays rather than the phase. Okay, and in fact, I heard this gravitational wave, like the speed of light, does corrupt the measured, so I have heard this argument saying that, why not? And I will show you that indeed, but we are dealing with coordinate time. So I'm in a TT coordinate. I'm not worrying about a gauge invariant quantity here. I'm in a TT coordinate. Indeed, we can show that the coordinate speed of light indeed changes. That's fine. We are not measuring, the proper velocity or proper time interval there. So these are the few things I will want to. So far, this is what I want to tell, and now I will quickly go to the other slide just to show you. I timed it, but I thought let me go to the other slide. This is some other lecture I gave somewhere else. Okay. Now, Control L. Excellent. I just want to show you why I call this plus and cross polarization. But if you have questions, don't ask me technical question on interferometry. I will have exactly the answer I gave him. So, okay. So, but since you may still wonder, I showed you that these are circular corrections, so elliptical deformation. But you may wonder, why should I call it plus or cross polarization? Well, for that you need to do this analysis. It is straightforward. So as we told about passing gravitational a bunch of particles. Oh, by the way, in that lecture, because I was lazy, it was on a short notice. I used the Roman indices from 0 to 3. So slightly flip. Okay. Well, if you can do that, it's not a big deal. So let xi, and this should be in your mind x mu nu and x mu and x mu plus chi mu. But in the same lecture I should not change notation, but sorry for that. So all you do is that you actually can compute one geodesic equation from the other, and that's how you get the geodesic deviation equation. So actually I can get the geodesic deviation equation for this psi I. It's a 4-vector. Yes, I will be done. So this is what I get. Actually, it's very easy to do this derivation. It's lengthy, but it's it's in a GR course you will do this. And I can imagine weak gravitational field. That's what I'm interested. So dx0 by d tau should be something like c. D square by d tau square will be d square by dt square. And then that spatial component of the geodesic deviation equation, that I put the alpha there, it's now alpha is only spatial components. This is what I get. And alpha and beta can be 1 and 2. And the gravitational wave is passing along the c direction. Particles lying in the wavefront should obviously in the xy plane. So these are the equation. I can actually do that. This becomes, when I look at these components, I get the 2 time derivatives of h alpha beta of times the chi of beta. A possible solution looks like this. That's fairly easy to figure out. And then I bring in my, one of the solution was, remember, a xy, a yx, right? I call 1, 2, 2, 1, it's the same. Then the solution looks like for the chi 1, because this was, alpha varies from 1 and 2 here. So I get chi 1 to be like this, chi 2 to be like this. Very nice. So what does it even mean? If the particle along the x direction, or x1 in this, moves outward, that's a plus. In the y direction, it goes negative, right? This goes out, that guy goes in. So x-axis goes out, y-axis particle comes closer to the origin. And that's what we call plus polarization. And for close polarization, you can do the same analysis. You get both the plus, but you will see slight difference here. The chi psi 1 depends on this, and like this, but the solution, this guy depends on chi 2 rather than chi 1 in the previous case. And that, if you plot, this is what you get. And that's what I call plus and cross polarization. And again, we are not measuring, so proper distance between the particles, as I keep telling you about that. And this is in general not independent of time. That's essentially what we were trying to measure by the phase differences. That's all. I think I'm pretty much done in time. Okay, thank you very much. Sorry for this, I should have converted that into proper notation. I said,
So there's plenty of time for questions. So please. Surely you have questions.
Okay, yes. Right. Yeah.
These are the analogs of the linear polarization modes of electromagnetic radiation.
Essentially, yes.
What does the cartoon look like for the analog of chiral gravitational waves?
Electrodynamics has the linear polarization, and then you get a combination for electric, circular and elliptic. Yeah.
Right. So for gravitational waves, we can also talk about chiral gravitational waves, which are the analogs of left and right circular polarization modes. What do the cartoons look like for chiral gravitational waves?
I mean, there are 6. I think there are this, theories where the graviton mass is not 0. I've seen those, cartoons with, there the waves are allowed to go in the longitudinal directions too, and other combinations. I don't have I can't reproduce them,
Guess-
but I
guess
can
my
dig out
guess
some.
was I just spin the ellipse around. Is
Yes,
that- okay.
and also the longitudinal modes will come in too. There may be theories where those modes are missing, but I am not familiar. This is the one off my head I can imagine.
Any other questions?
So in the previous slide where you did the expression between N and L, no, in the previous presentation.
Oh yeah, sure. I can bring it that. Where do you want me to go?
Like where you derive the expression N less than something
okay.
by, yeah.
Yeah, I can see. I think this is the one, yeah, here, right?
Yes, so for L equal to 4 kilometers, N is 200, and that's how we get that 750 kilometers.
Around,
So,
yeah, ballpark of 750,
roughly.
yeah.
So I was just wondering, so when we have detectors of 40 kilometers or any next generation detectors, then using this formula, N should be 20, and then the final length would be same. Then why do we get better sensitivities for, let's say, 40 kilometer Cosmic Explorer or Einstein telescopes?
Okay, there are multiple answers to this. These are not the equation for that. So one of the reasons they are much more sensitive is that their low frequency sensitivity can go all the way up to few hertz. Okay, so that's not easy for current LIGO. Okay, so and when you go down like that direction, right, your effective strain is the number of gravitational wave cycle, and that will substantially increase. You know what I mean by that? If you get essentially equal number of gravitational wave from something like 10 to 30 hertz than 30 to the coalescence. Okay, so the effective strain, which is h times square root of n, increases, and all you need is a factor of 10. Next generation is not going to make it factor of 100, it's just a factor of 10. Okay, that's one. I may not be fully correct here, and they have much better Poisson noise, this laser short noise, so they are also good enough at the high frequency, which has other implication. And then if I understand correctly that the thermal isolations and all that, so this can also come down. Okay, so there is, this knee frequency you're talking about, I think that also comes down. I think it's become around 50 or something like that. Again, I'm not an expert on this. My former postdoc, she's going to, very well, I should ask her. So she's in Nikkei, she's a faculty there and all that. Anyway, yeah, she should know. I should ask her. So why, how many passes of, I have no idea. I am not.
So using that cavity method, you actually reduced the length quite a bit. But I was thinking,
increase the length.
Decrease the length
of the
from
actual.
yes,
yeah,
yes.
yeah, actual. Oh, yeah, sure.
So is there any possibility? I think there are reasons why they should not do it. But you see, when light passes through some dense medium of, let's say, length L, actually light passes an effective amount distance is the actual distance of the length L, let's say, and multiplied by the refractive index, right?
So they're supposed to be vacuum.
Yes. So if the light passes through some dense medium of, let's say, refractive index n, the light actually travels an effective distance of nl in the vacuum.
Yeah,
right?
because you have a difference.
Yes.
Velocity of propagation.
So is there any possibility of putting something dense material in the length so that you can effectively increase the length?
Yeah, good question. I remember discussion in Germany because there are optics people in a place called Jena. they were talking about gravitational wave observatory in a chip, essentially optical media, but they were sensitive to very high frequencies. But they were talking about, creating such things. It's essentially based on something, the argument you said, but I have not bothered to follow it up. But again, for high frequency gravitational wave, they were thinking about, these things. Here, everything was around 100 hertz, but if you want to go beyond kilohertz and all that, and apparently there are some primordial black holes of, A4 paper size and all that, they should be able to do that. So, yeah.
Thanks.
I think, but I think I should also Google search what happened to those things.
Yeah. Thank you.
It's a very small doubt. Like there is a mention in the slide number 30, like the mass is set free above 100 hertz. So maybe I missed it. Like, I don't know, like why, like we are taking 100 hertz particularly.
Yeah, so I think I was trying to, so I made this line here. Okay, well, Alan Weinstein made this line here that mirrors have essentially suspended pendulums. Okay, so the pendulum, you have done this experiment, right? And then to measure, G and all that thing,
Yes,
right?
yes.
So for that, that guy has to be free. Yeah. Otherwise, how can it measure G, right? So for that, the argument is that, it has a natural, I think there's a word I just can't get. So that's this effect, what was this F naught called?
Natural frequency.
Huh?
Natural frequency.
Natural frequency, yeah, just missed my, yeah. So that natural frequency is around this. Okay. So then, it will be perturbed by other things. So what will happen is that if you perturb with other frequencies, it will damp.
Yeah.
Okay, yes. So that's the reason I'm looking at 100 times above that, so that I know that this pendulum, whatever the mass, right, it will be freely suspended. Okay. Because it will get disturbed around 1 hertz and all that, but other things get attenuated sufficiently that I can consider the guy as free. I mean, this is all comparative when you're trying to measure nuclear dimension, but still it works. And that's the amazing thing. And that's this 100 hertz I'm talking about. Okay? To make the mass free in my TT coordinates.
Thank you.
Okay. Final question, someone? It's almost 6, so I guess everyone's tired. If not, let's thank Guru again.
Thank you.
Kopu again.